So once again, let us proceed. Let us continue. We start with another topic referred to as DC transients. So there are some key factors you need to know about these DC transients. One of which is the definition of terms. In definition of terms, we are going to be talking about the transient. Another term we're going to be talking about is the time constant. Another term we're going to talk about the steady state value. Normally, for us to talk about the steady state value, then the current must be rising to a certain point where it settles between 2 to 5%. Then talk of the steady state value. But the time taken for the time to rise to reach the steady state values from 0 to reach the steady state value, when we talk about the time constant, that duration of time is referred to the time constant. But the transients is actually the rate at which, or the movement, the movement of current from maximum, from the steady state value to 0, or from 0 to the steady state value. That's what we talk about. That change is the transient. So let us refer to the transient. DC transients are quantities whose values are quantities, or whose values are quantities whose values are determined after a certain period when they get to reach steady states. So transient refers to the change that takes place when a quantity rises from 0 to steady state. Time constant is the period taken by a transient value to rise from 0 to steady state value, or vice versa. The meaning of vice versa is from the steady state to 0. So from there, then we are going to be talking about the types of DC transient circuits. The types of DC transient circuits. Include Roman 1 is RC circuits. Roman 2 is LR circuits. Roman 3 is RLC circuits. So we shall be dealing with the RC circuits. So in this circuit, we must be able to understand about the charging and discharging. And in this case, we shall have a circuit that appears this way. So the first thing we need to understand is you must be able to understand how you shall be charging and discharging the circuits. So the resistor here, what I refer to as R of S, and this R of L. The resistor referred to R of S be used for charging the capacitor. And after charging the capacitor, we must also understand how the capacitor is going to be discharged. In that case, then we shall be moving the switch to terminal point B. If this is A and this is B. For us discharge, we shall be able to move the switch to terminal point B so that the capacitor discharges through the resistor RL. So this is the basic circuit that we used for charging and discharging of the capacitor. So we need to be able to derive equations and prove to these equations that this circuit can also is real by charging and discharging the capacitor. So basically we shall be using whatever referred to as Kirchhoff's voltage law, and also to be able to understand what current flows in this circuit. So we shall be able to use the Kirchhoff's current law. So during charging, then from Kirchhoff's voltage law, V of S is supposed to be V of R plus V of C. And we also know that V of S is supposed to be I of R plus V of C. But according to our understanding and according to how the equations are done, the current that is due to a transient current is given by. But current I is supposed to be C dVC over dt. This is the current that's given by transient. So when you have this, we shall be able to replace the value of I in the equation here. So that we shall have V of S is supposed to be C, I is C, then we shall have R dVC dt plus VC. dVC dt plus VC. Then we collect the term together, we shall have Vs minus VC is supposed to be CR dVC dt. When by separating variables, we shall have this as dt over CR is supposed to be dVC over Vs minus VC. So for us, we have this equation here. Then by integrating both sides, by integrating both sides respectively, we shall have integral of dt over CR, integral of dVC over Vs minus VC. On the left hand side, we shall have T over CR plus a constant, and this other side we shall have ln of Vs minus Vc. For us to get to ln, when you look at the numerator of the integral part at this point, we are going to realize that dVc is a function of differential of Vc. And by default, then, because this part is contained in the denominator, we shall have an L, and this is given here is a power of 1. We shall have this as the ln of Vs minus Vc. From there, then we replace the initial conditions. replacing the initial condition. We know as at start of charging, T is given as 0, and the voltage across the capacitor is also 0 at the start of charging. Those are the conditions for us to replace. We replace that in the initial condition. Then you shall have that one as 0 plus K is supposed to be giving us ln of Vs minus 0. So K is supposed to be ln of Vs. We have that as a formula. Then replacing that, T over Cr plus K is ln of Vs, ln of Vs must be equal to ln of Vs minus Vc. We collect like terms together. T over Cr is supposed to be ln of Vs minus Vc minus ln of Vs. By using logarithmic ratios, by using the law of logarithms, we shall be subtracting that, and that means we shall be able to divide. So by using the law of logarithms, then we shall have T over Cr is supposed to be ln of Vs minus Vc over Vs. So getting the ln of both sides, natural logs, getting natural logs, logarithm of both sides, we shall have this as 1 over e T over Cr supposed to be Vs minus Vc over Vs. This name becomes E minus T over Cr supposed to be Vs minus Vc over Vs. Multiply across this, shall have Vs E minus T over Cr supposed to be Vs minus Vc. They collect like terms together. They collect like terms together, shall have Vc supposed to be Vs minus Vs E minus T over Cr. That means Vc is supposed to be Vs into 1 minus E minus T over Cr. So this is the equation meant for charging the capacitor. So that's the equation we are supposed to arrive at and derive that, get that point. So we can be able to sketch this using a curve. So one of the things we must assume when sketching this, sketching the above equation, we have to sketch the maximum and we have to sketch the values of the maximum and minimum values. So when this is the sketch, this is time and this is the voltage. So when time t is equals to 0 from the expression, when time t is equals to 0, that means our supply voltage will be 0. So we shall be at this point here. Because the meaning of t raised to power 0 is 1. 1 minus 1 is 0, then V is supposed to be 0. We shall be at this point, at the starting point. When time t is equals to maximum value or infinite value, then e raised to power infinite is supposed to be 0. 1 minus 0, we shall get s. So at the point V, we shall have a maximum point here, which we shall refer to as steady state. So this value is Vc is equals to Vs. Vc is equals to Vs at this point, and shall have our curve looking like this. So this is Vc is supposed to be Vs into 1 minus E minus tau over Cr. So in all this case, Cr refers to the time constant. Cr is referred to as the time constant. So we are also supposed to get the value of the voltage across the resistor. So this is the value, the voltage across the capacitor, but we're supposed to get the value of the voltage across the resistor and also the current. So sketch here. So determining the curve. The curve for the charging current. So first recall, I is supposed to be C dVc dt. We have that in mind. C dVc dt. So I, that means we shall have C d dt. But what is our Vc? Our Vc from the equation was given as Vs into 1 minus E minus T over Cr. So put Vs is constant and differentiate the rest with respect to dt. We shall have this as C Vs dot C. Differentiate then that one, we shall have this as that is, we shall have minus minus E. Differentiate this, there's a minus here. There's a minus here. This is a minus, and differentiate this, we get a minus. Minus E T over Cr. They differentiate the power there, we must get another minus, dot minus 1 over Cr. I hope you're okay. We differentiate this, we get 1 over C, minus 1 over Cr, this 1 over Cr. This minus and minus here cancels. Minus times a minus here becomes a plus, because that becomes a plus. Then we shall have our Vs C, we have C over R, E minus T over Cr. C and C cancel out. Then we shall have our equation as Vs over R, E minus T over Cr. But what is Vs? This is I. Vs over R gives us what? The steady state current. But Vs over R gives us the steady state current, whatever to us the DC current. Then I is supposed to be I E minus T over Cr. Then you can also sketch that from the analysis. You also sketch that the curve now appears to be, this is time, and this is referred to as I. When the time is 0, what do we expect of a maximum value? T is n numbers per 0 and get I. So we shall expect our I to be here. When time is maximum, then this will also be 0. So we shall expect our curve to be this way. So this is supposed to be I, is supposed to be I E minus T over CR. That's how the curve for charging current appears to be. Then we are going to now to get to the curve for determining the resistor. So we shall be able to do that also. So the voltage across the resistor is given by VR is supposed to be IR. But what is our I? Our I is there is given by, but I is given by IE minus T over CR. We come at the place that we shall have I R E minus T over CR. Well, that's that then, but I times V gives us the VS. Then VR is supposed to be VS E minus T over CR. We also sketch its curve. So when T is supposed to be 0, what then is that? We shall have a curve appearing this way. So this is VR supposed to be VS E minus T over CR. So these are the curves you are expected to draw during charging and discharging. I remember we have drawn the three parameters, the one for the capacitor, the one for the resistor, and the one for the current. So all of them appear this way. This is only happens during the charging process. Then you have now gone to the discharging process. So this is an example of a capacitor question that involves the charging of a capacitor, and basically we are given a 4 microfarad capacitor that is connected with 100 kilo ohms in series, and the supply is given as 20 volts. So we are being asked to determine the time constant, the initial charging current, the initial rate of growth of the potential difference across the capacitor, and the potential difference across the capacitor after time equal to time constant, and the time taken for the capacitor voltage to reach 18 volts from the time the switch is connected. So the first thing we have to determine is the time constant. So this is the solution. Time constant, what I refer to as tau, is normally given by CR. That's the formula for time constant, which means that we shall have 4 times 10 power minus 6 microfarads minus 6 times the resistor is 100 times 10 power 100 times 10 power 3. We get the time constant. This 4 times 10 power minus 6. is 0.4. It's 0.4 seconds. That is time constant. We are done with the first part. The second part is the initial charging current. Initial charging current, what I refer to as the I. Initial charging current, I is supposed to be V over R. Then shall have V as 20 volts over R is 100 times 10 power 3. And this gives us 0.2 milliamps. So we're going to go to the third part of that, is the initial rate of growth of the potential difference across the initial rate of growth of the potential difference across the capacitor. Roman 3. Rate of growth of potential difference across the capacitor. One of the things we're supposed to remember is is the formula for charging current. I is supposed to be C dVc dt. From this formula itself, dVc dt gives us the rate of change of the voltage across the capacitor. That means that our dVc, our dt is supposed to be I over C. And our I is whatever we have found out to be. I is whatever we find out to be 0.2 milliamps. I is down there. 0.2 times 10 minus 3 is milliamps. Divide the capacitor is 4 times 10 power minus 6. 4 times 10 power minus 6. Then we shall have this as shall have this as 50 volts per second. 50 volts per second raised to -1. So we go to Roman 4. We have been told that the potential difference across the capacitor after time equal to time constant. The Vc is supposed to be Vs into 1 minus E T over Cr. But we have been told that T is equals to Cr. That means that our formula will be reduced to Vs into 1 minus E minus 1. So this Vs was given as 20 volts, 1 minus E minus 1. What do we get as the Vc? That is 12.64 volts. Then the Roman 5 is a bit told the time taken for the capacitor voltage to reach 18 volts. the time taken for the capacitor voltage to reach 18 volts. That means our VC is supposed to be 18 volts. So VC is supposed to be Vs into 1 minus E minus C over tau over CR. So we shall have 18 volts is supposed to be 20 into 1 minus E minus T is what we are looking for, but the time constant, we have it in our values at 0.4 seconds. Time constant is 0.4 seconds. So we do 18 divided by 20 minus 1. So 18 divided by 20 minus 1 is equal to minus E minus T over 0.4 seconds. Then that is minus 0.1 is supposed to be minus E minus T over 0.4. So minus and minus cancel, so that we have 0.1 is supposed to be E minus T over 0.4. So T over 0.4 is supposed to be ln of 0.1. And then ln of 0.1. This becomes minus 2.30 is supposed to be minus T over 0.4. So cross multiply and minus cancel out. T is supposed to be (0.92 seconds). So that's the solution for the entire question. So we're going to go to the process of discharging the capacitor and the equations. So during the discharging of the capacitor, in this case, our capacitor is now connected to the RL in the diagram that we used, so that you are able to discharge the capacitor voltage through the resistor RL. Then, during the charging of the capacitor, then from Kirchhoff's voltage law, VC plus VR is supposed to be given as 0, because our final voltage is supposed to be 0. Our source voltage is supposed to be 0. We are not discharging that. So remember, this VC is supposed to be VC plus IR. Supposed to be 0. I recall that I is supposed to be C dVC dt. So this VC plus CR dVC dt is supposed to give us 0. So VC or CR dVC dt is equal to minus VC. So separate the variables. Separate the variables, shall have VC shall have minus VC over, you shall have dVC, you shall have dVC over VC is supposed to be dt over CR with a minus. So integrating both sides, shall have ln of VC is tau over minus tau over CR plus a constant. Then from there, we are going to replace at the time of discharge. what happens to our formula. At the instant of discharging, at the start of discharge, at the start of discharge, T is supposed to be 0 and Vc is supposed to be Vs. That means that ln of Vs is supposed to be 0 plus a constant. So my K is supposed to be ln of Vs. Replacing K in the equation, ln of Vc is equals to T minus T over Cr plus ln of Vs. We collect like terms together using the law of logarithm. Using the law of logarithms, we shall have ln of Vs, ln of Vc, ln of Vs, Vc, ln of Vc minus ln of Vs is supposed to be minus T over Cr. So ln of Vc over Vs is supposed to be T over Cr minus. So getting natural logs, getting natural logarithms of both sides. We'll have Vc over Vs. Then we shall have E minus T over Cr. So Vc is supposed to be Vs E minus T over Cr. So we are able to plot this. We draw the curve T, and this is Vc. So when T is equals to 0, Vc is equals to Vs. So at this point here, Vc is equals to Vs. And when T is equals to infinity, that's 0, then you shall have that. So you shall have a formula appearing to this way. So this is Vc is equals to Vs E minus T over Cr. We can get the voltage across the resistor. The voltage across the resistor. VR is supposed to be IR. The VR is supposed to be IR. But what is I? Then we must first look for I. I is supposed to be C dVc dt. But Vc is given by this, which means that IC d dt, our Vc is supposed to be given as Vs E minus T over Cr. That means that we shall have this as Vs C Vs over, if we differentiate that, we shall be getting our value there as Cr but it's a minus. It's a minus because of minus TCR, E minus T over CR. C and C cancel. That means our I is supposed to be V over S over R is supposed to be I, E minus, there's a minus here, T over CR. This minus means that we are discharging the capacitor. And when you plot that, then our curve is going to be looking like this way. That's a minus. We're going through a minus, we're coming towards a 0. So we shall be having our current. When T is supposed to be 0, then I is supposed to be maximum. Then shall be, this is what explains, give us I is supposed to be. We are in the negative side, we're going toward the positive side. E, IE minus T over CR. Then for, this is T and this minus I. This is 0. That part is I. So VR is supposed to be IR. VR is supposed to be IR. Then I is supposed to be I multiplied by R multiplied by E minus T over CR. So our VR is supposed to be Vs E minus T over CR. Equally, its equation is going to look like this. This is minus V of S. This is 0. This is T. So in the event that you are drawing this on the upper side of the curve, then it means that if this is going to be in the numerator here to be positive, then this curve is going to be having that shape. That is the event that you have drawn it on the numerator, on the upper side of the positive side of the plane. And also this one, they will also be having the similar scenario. So the broken sides, actually, if you had drawn it on the positive part of the plane, we shall have this. So this basically marks all the charging and discharging process of the capacitor. So in this case, we shall only do one example, that is with reference to charging and discharging. So I apply both cases in this manner. So this is an example of a circuit that employs both charging and discharging. And you look at these conditions, we have given the position of the switch, and we are being asked to be able to, first when the switch is connected to terminal B, and also another instance when the switch is connected to terminal C, what are the different values. So the first part tells us about if the switch is moved to position B at an instant time, it goes to 0. Then you're being asked to determine the voltage across the capacitor at time t is equal to 1.5 seconds. The first thing you have to know is we have to get the time constant for this circuit. And the time constant for this circuit should be given when the switch is connected to point B. So when we get this, so that we are able to get the formula. Find the time constant. We are dealing with part 1 of the equation. the time constant tau is given by CR, which is supposed to be 10 times 10 minus 6 times R is 0.5 times 10 power 6. So this becomes 5 seconds. Goes minus 6 positive cancel this 5 seconds. That is the time constant. Then you can now proceed on and determine the voltage across the capacitor at time t. Therefore, the voltage across the capacitor at time t is equals to 1.5 seconds is given by Vc is supposed to be Vs into 1 minus E minus T over Cr. Remember, this time we are charging the capacitor 10 microfarads. So Vs was given by the voltage connected is 50 volts into 1 minus E. The time you are given is 1.5 seconds over the time constant there is 5 seconds. Then we are able to determine this from our calculations. That is 12.959 volts. So the part 1 of the question is fully answered. And part 2 of the question, we are going to go part 2 of the question. The time taken for the voltage to fall to time taken for the voltage to fall to 80% of the final value. The first thing, you get 80% of the final value. The final value is 50 volts. The final value is 50 volts, but 80% of the final value, 80% should be equivalent to 0.8 times 50. This is 40 volts. The time taken for that to reach. So we know that when the capacitor is discharging, Vc is supposed to be Vs into Ct minus Cr. Remember our formula, and Vc is given by 40, and Vs is 50. E minus T is 5 seconds here. So that is 40 over 50. Supposed to be E minus T over 5. 40 divided by 50. So this is 0.8 is supposed to be E minus T over 5. So ln of 0.8 ln of 0.8 is equals to E minus T over 5, and this is supposed to be minus 0.223 is supposed to be minus T over 5. Minus and minus cancel, so T we shall have that as times 5. 1.115, which is approximately equals to 1.12 seconds. That is the final answer for that question. So, thanks for attending the sessions. We are coming to the end of the first part of the DC transients in terms of the CR circuits. In the next session, we shall be dealing with the LR circuits, and we shall also work with the examples and the circuits. So let us avail ourselves for the next session as we proceed, as we continue understanding on the effects of analysis on circuits or electrical circuits. Then thank you. JEMSHAH.